Okay, this is where we left off last time when we figured out concentrations. And again, reaction order, I hope you guys understood that. I had that worksheet and that video to show you. But again, you're just comparing a change, okay? Looking at the change in concentration. This one has to stay the same. This one changes. So if we do this one 1 to 2, because I got to go where this is the same. So 1 to 2 goes from 4 to 16. So this multiplies by 2, this multiplies by 4. That would be, that would be twice as much. That would be a second order. And then B, this is where it changes, and this one stays the same, and the rate stays the same. So this is a 0. Okay. So using this data, the rate law, we want to do the rate law, the rate constant, and the rate of reaction. Well, the rate of reaction is pretty simple. Like I said, for A, it's 2, and for B, it's 0. Okay, so the rate law is where we use the formula rate equals K times the concentrations of our two reactants to the whatever power they are. Okay, then once we find K, then we can figure out these. Now they're asking us to give concentrations that aren't up there, and we're supposed to figure out the rate. Okay, so we did the rate. A is 2 because it doubles, so it's 4 times as much, and B is 0 because the concentration didn't change. So we got to remember 2 and 0. And again, that's what we did last part. Hopefully you guys got a good handle on that. Okay, so rate constant is K. We got to find K. It's A, and it was actually should probably put the M and the N up here because that's the reaction order. So the rate constant, we can get the rate from here, and we can get the concentrations from here, and we know what these are too. So we can just fill them in. Okay, we have to solve for K. And again, you can use any one of these experiments. Some people just do the first one, some do the last. You're going to get the same answer, so it doesn't matter which one you use. Okay, so to solve for K, I'm going to take my rate, which is 4.0 times 10 to the 5th, and then I'm going to take my constant A, or my concentration of A, and I don't have to do B, because if it's 0, anything to the 0 power is just 1. So if anytime you have one of these concentrations that are 0, you don't have to include them. It's like, thanks, that makes it easier. So really all you do is you take the rate and you divide by the concentrations. So I took 4.0 times 10 to the 5th, that was my rate, divided by A to the second, because again, that was its reaction order. And so this is what I get, 4.0 times 10 to the negative third. This is my K. This is my rate constant, okay? So again, when you're trying to find it, really what you do is you take the rate and you divide by the concentrations to whatever reaction, whatever power order they are. And again, if they're 0, like B was, you don't have to include it, because anything to the 0 power is 1. Okay, so this is, now what I want to do is, the second part of my question was, okay, once I find K, if I have my A equal to 0.05 and my B equal to 0.1, what is my new rate? So in other words, I can find this now that I found K. So I just plug in the numbers. I know K is 4.10, or 4 times 10 to the negative third. I just figured that out. It says my concentration for A is 0.05, and again, it's to the second power. I don't have to include B because B is 0. It's basically not included in there. It doesn't affect the rate. And so then you just multiply and you get this. So the first thing we did was find the reaction orders, 2 and 0. Then we found K by plugging in the numbers. And then we can use K, we can change these concentrations to pretty much anything we want. And we can find the rate by using K once we find it. And if you did 2 instead of 1, you would get the same answer. And it doesn't matter which one of the experiments you use. You're going to get the same answer. Okay? Okay, so here's another one. The following data was measured for a reaction. We got nitric acid plus hydrogen. Okay, so we're just supposed to determine the rate law for this reaction, calculate the rate constants, and that so on. Okay, so first thing we got to do, let's find our reaction. Okay. Let's see, from here to here it doubles, and here to here. So I got to use experiment 1 to 3 to find out NO. Because here it doubles, here it stays the same. So 1 here. What happens to my rate? goes from 1.23 to 4.92. So it quadruples, right? If I take this divided by this, I'm going to get 4. So this doubles, and this goes 4. So we know NO is 2. Okay, now let's find H2. Here it goes from here to here. It doubles. That stays the same, so I can use this one. Here to here doubles, and here it doubles. So this doubles, this is 2, and this is 2, so my reaction order is 1. So NO is 2, and H2 is 1. Okay? That's the first thing I would do. Okay? Then, now I want my rate constant. So I'm going to take my rate, and again, you can take whichever reaction you want. You're going to take your rate. Oh, I use the second one. And then I'm going to divide by, oh, I should have this over the third, sorry. This is up here, you guys, -3. Okay, and then I'm going to take my concentration. So if I'm doing the second one, I take my concentration of NO, which is 0.1, and it was a second order, so I raise it to the second power. And then this one is 0.2, and it was to the first power, okay? So basically, I'm going to take this, and I'm going to divide by this, and I get 1.23 meters per second. That's my rate. Or that's my K, my rate constant, I should say. Now I can use this number because they want me to change the concentrations of this to 0.05 and the concentration of this to 1.5. And now I want to find the rate. So I take my rate constant that I just figured out, and then I multiply it by these. So I take my 1.23 that I just figured out. It says now I want it to be 0.05 to the second. And this one is going to be 0.1, and again, it's to the first, so it's just 0.15, sorry. When I multiply these all out, this is what I get. So now this is my new rate. So when you're doing this, you take the information you know to find K, and basically, again, you take the rate and you divide by these two concentrations to their powers, and then you use that number. You can change any of these concentrations to whatever you want, and you can find your new rate because you've got the constant. So you just multiply, okay? So that's how you do reaction rate. First, you got to find their order, and then you can use that to figure out the rate constant, which is K, and then you can use K to find out, you can change these numbers to whatever you need, and you can find out what the rate's going to be, okay? Okay, so when you're looking at K, that's the rate constant, what does it mean? It's often used to determine a relative rate of a reaction. Again, we did that. If you're looking at it, if K is kind of equal to times 10 to the -9th or higher, so if it was like 1.2 times 10 to the negative, or 1.2 times 10 to the 9th, this would be a super, super fast reaction. If it was 10 to the 8th, 10 to the 7th, it would be not quite as fast, but it'd still be pretty good. If K is, just 10, like in this case, we got 1.23 for that. That would be a much slower reaction. So K can help you determine just by looking at it if it's a fast reaction or if it's a slow reaction. Okay. What are some of the things that affect reaction rate? Well, one thing is temperature. Again, if you increase the temperature, usually your reaction rate is going to increase. How many collisions you have, and that's kind of related to temperature, because if you increase the temperature, you increase the kinetic energy, and then they're going to bang into each other more, and then the reaction is going to happen faster. How the molecules are orientated, because remember, we want them to be orientated so they can bang into each other. If you have a positive and a negative, they're attracted to each other. We want them to bang into each other, so we don't want them to have the same. And then something called activation energy, and that one I'll talk more about. But activation energy is the energy that you need to overcome in order for the reaction to occur. Some reactions occur spontaneous. You put two things together and the reaction just happens. Sometimes they'll just sit there and you have to do something to get them started. And that's what they call the activation energy. If the activation energy is high, that means you have to do a lot to get that reaction to occur. If it's low, then it's going to happen pretty quick. Okay, so activation energy, it's kind of, its name kind of tells you what it is. It's the energy needed to get a reaction going, get it activated, okay? So when we talk about temperature, generally, again, as your temperature increases, your rate increases, because now you got your particles moving around faster. Here they're showing, I think this is like a glow stick, okay? In cold water, it doesn't glow nearly as well as it does in hot water, okay? So the rate constant is temperature dependent, okay? So if you increase it, you'll also if you increase the temperature, you'll increase the rate, the K, the rate constant, okay? And here they're showing, I'm sorry, I'm in part of it, but you can see as the temperature increases, this is K over here, this is the rate constant, it also increases, okay? Rate doubles, constant doubles approximately for every 10 degrees rise in Celsius. So, you know, if your rate was here like 1 times 10 to the third at what, 230, then when I go up to 235, when I jumped up to 245, look at that, now it's 2 times 10. And then if I go to 255, then it's 3 times. So approximately every time you raise the temperature 10 degrees, you increase the rate constant, you double it. Okay. When we talk about frequency of collisions, again, the more they collide into each other, the more they react with each other. And gases, of course, do this the best because they're moving the fastest, so they're going to smash into each other more. Okay, so molecules have to collide to react. Okay, and if they're not banging into each other, then they're not reacting. They're staying, and you know, you got nothing going on. So the more collisions you have, the more reactions that are going to occur. That's what you want to happen. And again, that's why when you increase temperature, that happens because they're moving faster, so they're going to bang into each other more. Okay, so if there are more molecules, the reaction rate is faster. So again, if you want to increase the frequency, add more reactant, because now you have more molecules to bang into each other. Okay, so in a chemical reaction, really what happens in a chemical reaction, bonds are broken and new bonds are formed. So the more they can bang into each other, the more they collide with each other, the more this is going to happen. So again, if you want to increase the frequency of collisions, what you can do is you collide with each other. Okay, the more they collide, the more they react. So if you increase the amount of reactants, then that's going to happen. Okay, and another thing is the orientation of the molecules. Okay, what will happen is here there's, you know, they bang into each other and they stick together. And then what happens now, this bond's broken, so now you get 2 new substances. Down here, if it bangs into each other, it just bangs and then comes back out and it doesn't form a bond, then that's not an effective collision. So they have to get orientated right. So here the green had to go with the green. And then they stuck together and you got 2 new compounds. Here what happened when it was orientated, when it flipped over and you had the red and the green, they banged into each other, but they didn't bond. So you didn't get a good collision. So the orientation has to be right for, the molecules have to be aligned properly if you want to lead to chemical reactions. Okay. So because bonds have to be, oops, sorry, you guys. Bonds have to be broken and reformed. So again, this one comes, these two are going to stick together. Now you're going to get 2 new substances. The bond happens. Here, because this is flipped over, these two don't bond with each other. So it just bangs into it and then takes off, and they're still both the same. So nothing happened here. So that's what they mean by orientation of molecules. They have to be orientated right so that they'll form a bond. If they're not, they don't. Okay. So and I think I'm going to quit there because the next slide starts to talk about activation energy, and I want to do that as a separate entity. So we're going to quit right here, and then we're going to start working on some of those, trying to find the Ks, the reaction laws. So we'll quit on this slide. Okay.